In this video, we will be learning how to solve exponential and logarithmic equations. Right, basically, if you have an exponential equation, you can undo it by taking the logarithm of both sides, log base a. So as long as the logarithms have the same base on both sides of the equation, you can do that to get the x term out of the exponent. Like this example, 7 raised to the power of x equals 12. Now, since if you're using a TI 83 or 84, the only two logarithms are the common log and natural log that you can use. So, do that, you could do ln of both sides. ln of 7x equals ln of 12. Now, one of those properties of logarithms says that you can move the x out to the front, since that's the exponent, so it's x times natural log of 7 equals natural log of 12. So now, to solve for x, you have to divide both sides by natural log of 7. So x is equal to ln of 12 divided by ln of 7. And it says round to the thousand, so if you type that in your calculator, you will find the thing should be about 1.277. If you had done the common log of both sides at the beginning instead of natural log, you should still get the same answer. And before we move on to the next example, I just want to iterate something. If you have natural log of 12 in the numerator, divided by natural log of 7, that is not the same as natural log of 12 over 7. Those are not the same thing. Please do not do that. Alright, now that that's been stated, we can move on to the next example. Alright, solve this exponential equation. 3 raised to the power of 2x minus 1 equals 0.4 raised to the power of x plus 2. It says to give the solution to the nearest thousandth, meaning to 3 decimal places. So, let's start off by writing the equation. 3 to the power of 2x minus 1 is equal to 0.4 raised to the power of x plus 2. Now, to get the x terms out of the exponent, you would need to do either natural log or common log of both sides. Since we did natural log last time, let's do common log this time. Do common log of both sides and you get 2x minus 1, move the exponent in front, times natural log of 3, or not natural log, common log, equals, and that should be x plus 2 times ln of, I did it again, common log of 0.4. So now if you want to distribute the log base 3 to the 2x or not log base 3, log of 3 to the 2x and log of 3 to the minus 1, you would have 2x log of 3, and then minus 1 times log of 3 would be minus log of 3, equals, distribute the log of 0.4 to x into the positive 2, so that'd be equal to it'd be x log of 0.4 plus 2 times log of 0.4. So now what we need to do is get the x terms on the same side. We can, since that's positive x times log of 0.4, we can subtract that. So do minus x times log of 0.4 on both sides. And then also get the non-x terms to the right, so add log of 3 to both sides. You should end up with, on the left-hand side, 2x natural log of 3 minus x times log of 0.4 equals, on the right-hand side, 2 ln or natural log of 0.4 plus log of 0, or log of 3. So if you notice on the left-hand side, you can factor an x out, so that'd be x times, you're left with 2 log of 3 minus log of 0.4 equals this equals the right-hand side. 2 ln of, or natural log, I keep doing that, plus ln of 3. Now, to solve for x, since we're multiplying x by this side, it might help if we go ahead and combine these so it's not as much to write. Now this 2, since it's in front of the 3, that can be moved to the exponent. And since we're subtracting, we could actually combine those into one logarithm and divide, since they both have the same base. So instead of 2 log of 3, that's the same as 3 squared. Log of 3 squared, and since we're subtracting those, the right-hand side simplifies to x times log of 3 squared divided by log of, actually, remember we're combining them, so it wouldn't even be log, it'd be log of 3 squared over 4 equals, since we're adding those, we can move that 2 to an exponent, so that'd be log of 0.4 squared. And since we were adding the right-hand side, that would be log of .4 squared times 3. Or to write it neater, x times log of 3 squared is 9 divided by log of, that'd be 0.4. So 9 divided by 0.4, which would be 9 divided by 0.4, if you type that in your calculator, would actually be 22.5. Equals 0.4 squared. 0.4 squared times 3. 0.4 squared would be 0.16 times 3 would be log of 0.48. So now to solve for x, you have to divide both sides by log of 22.5. So if you type that into your calculator, log of 0.48 divided by log of 22.5. Remember, it wants it to the nearest thousand, so to 3 decimal places. So it'd be approximately negative 0.236. Alright, for the next example, it says solve each equation, give solutions to 3 decimal places. So, e to the power of x squared equals 200. And for part B, e to the power of 2x plus 1 times e to the power of negative 4x equals 3 times e. Alright, so what we can do would be, for part A, since the x term is in an exponent and the base is e, you could do log base e or ln. Remember, as a side note, ln of x is the same as log base e of x. So you would do log base e to get it out of the exponent, since the base is e, or you could just type in ln. So ln of e to the power of x squared equals ln of 200. Alright, that moves out in front, so you have x squared times natural log of e equals ln of 200. Now, another side note that I'm going to quickly write down and then erase. Ln of e is the same as log base e of e. Remember, whenever the base and the input are the same, they're equal to 1. So, ln of e is equal to 1. X squared times 1 is x squared. Equals natural log of 200. And as far as I'm concerned, you can go from this step to this step. If you get good enough at this, you don't have to stop. You don't have to do this step. But anyway, now that we have an equation, x squared equals ln of 200. So now we take the square root of both sides. So x is equal to positive or negative square root of natural log of 200. And we want the solution to 3 decimal places, so it's equal to positive or negative 2.302. So that's positive or negative 2.302. And since it's an exponential, we do want both solutions. If it were a logarithmic equation, we might not want the negative. So now for part B. E to the power of 2x plus 1 times e to the power of negative 4x equals 3 times e. Alright, so let's go ahead and combine these into a single exponential. Now, if you're multiplying two things that have the same base, see how on the left hand side they both have a base of e, you can add the exponents. So that would be the same as e to the power of 2x plus 1 and then plus negative 4x equals 3 times e. Now 2x, that should be plus negative 4x. 2x plus negative 4x would be negative 2x plus 1 equals, then e to the power of negative 2x plus 1 equals 3 times e. Now it'll be a lot easier to use the natural log if we can get rid of the e on the right hand side. Since we're multiplying, let's divide by e on both sides. Those cancel out, so on the right hand side you're just left with 3. On the left-hand side, keep in mind that e on the bottom, since it's understood to have an exponent of 1 because there's no exponent given. So, when you're dividing two things that have the same base, like on the left-hand side we're both dividing things that have a base of e, you actually subtract the exponents. So it's e to a power of negative 2x plus 1, and then we have to subtract the exponent of the term on the bottom, so minus positive 1. That means we would end up with e to a power of negative 2x equals 3. Now that we just have one exponential term, we can do ln of both sides. Now we have ln of e raised to some exponent, so like I said before, you can just skip to writing it like this, negative 2x for the left-hand side equals ln of 3. Now, since we're multiplying x by negative 2, you would need to divide by negative 2. So x is equal to ln of 3 divided by negative 2, which would be, if you round it to 3 decimal places, x would be approximately negative 0.549. So now we're told to solve e to a power of 2x minus 4 times e to a power of x equals, or plus 3 equals 0, and give the exact values for x. What that means is that if we end up for any values of x involving a natural log, we're not going to type it into the calculator. We're just going to leave it as it is. So for this, e to a power of 2x. Again, before you start working on it, I want to remind you of a rule of exponents. When you have one exponent raised to another, you can just multiply the exponents. X to a power of a times b. So since for the first term, since we're multiplying the 2 and the x, we could rewrite that as one exponent being raised to the other. We could rewrite that as just e to a power of x raised again to the second, because x times 2 gives you 2x, minus 4 times e to the power of x plus 3 equals 0. Now let me erase this. Now, you notice we have something squared minus 4 times that something plus 3 equals 0. So if we pick some letter other than x, say u, let u equal e to a power of x. Then this quadratic instead of e to the x raised to the second, that would just be u raised to the second. Instead of minus 4 times e to the power of x, it'd be 4 times u plus 3 equals 0. So what we can do from here is factor it down. Since the second times addition, we want the factors of 3 that add to give you 4. And of course, those would be 1 and 3, because those are the only factors. Now, since the second sign is addition, both the factors are the same sign. Since the first sign is minus, that means they're both minus. So it's u minus 1 times u minus 3. So now if we take each of those and set them equal to 0, u minus 1 equals 0 and u minus 3 equals 0. That means u is equal to 1 and u is equal to 3. However, keep in mind the problem wasn't asking us for values of u. It's asking us for values of x. So we have to plug back in u equals e to the power of x. So we have to plug those back in. instead of u equals 1, we'd have e to the power of x. And then e to the power of x is equal to 3. Now, if you take natural log of both sides for the first one, you should end up with ln of e to the power of x equals natural log of 1. And this simplifies to x equals natural log of 1. And when you take logarithm of 1, that always simplifies to 0. Even if you did common log of 1, that would still be equal to 0. So your first x value is 0. Now we gotta solve the second one, e to the power of x equals 3. If you do natural log of both sides for that, it'd be ln of e to the power of x equals ln of 3. The left-hand side simplifies to just x, so x equals ln of 3. Now it said it wanted the exact value. The exact value would be ln of 3. If you type that to the calculator, that would just be an approximation. So you leave it like this, so x is equal to 3. And also remember, x is equal to 0. Alright. So it says solve the equation and give exact values. So for part A, since we have ln of x, you can start off by dividing both sides by 7. So for part A, ln of x, the 7s would cancel out, so you'd have ln of x equals 4. Now we need to get rid of that x inside the logarithm. So you would just, actually what you could do is just rewrite it as an exponential. Remember, ln of x is the same as log base e of x equals 4. So you could rewrite this as just e, take the base of your logarithm, that's the same as the base of your exponent, e to a power of 4 gives you the input of the logarithm, x. So your first value of x is e to the 4th power. Since e is a never-ending decimal, it's an irrational number, we're just going to leave it as e to the 4th because it says it wants the exact value. Alright, for part B, log base 2 of x to the 3rd minus 19 equals 3. Again, since we have a logarithmic equation, let's change it to an exponential. Your base of your exponent would be the same as the base of your logarithm, so it would be 2 raised to a power of 3 equals the stuff on the inside, x to the 3rd minus 19. So now we have the x out of the logarithm. Now to solve for x, we add 19 to both sides. Remember, 2 to the 3rd is 8, plus 19 gives you 27. 27 equals x to the 3rd. Since we have x to the 3rd, we take the cubed root of both sides. The cubed root of positive 27 would be positive 3. Now, here's another example. It says solve log of x plus 6 minus log of 2 equals log of x, and give the exact value. Alright. If you notice for this one, it says it has a log on each side. So we'll deal with that in a minute. But if you notice the left-hand side, we're subtracting two logs that have the same base. Since we're subtracting two logs that have the same base, we can combine them into one logarithm. and then divide. That equals log of x. Now, since we have two things that are equal, and the logarithms have the same base, that means their inputs must be equal. The x plus 6 times x plus 2 equals log, not log of x, it just equals x. So, to solve this, we would need to get rid of the denominator, so multiply by 2. Or multiply by x plus 2 on both sides. So that would cancel those out. Times x plus 2 over 1. I put it over once just so you could see that the x plus 2 actually goes with the numerator up here. And that's why it would cancel out. But anyway, if you do that, or after you do that, you will end up with x plus 6 equals x times x plus 2. Now if you distribute, x times x is x squared, x times 2 would be 2x. That equals x plus 6. Now if you subtract x from both sides, and subtract 6 from both sides, everything cancels out on the left-hand side. So you're left with 0 equals x squared, 2x minus x would be positive x, and then minus 6. Now we want since the second sign is minus, we want the factors of 6 that subtract to give you 1. And those two factors would be 3 and 2. Since the second sign is minus, that means they're different signs. One of these factors will be addition, one will be subtraction. To figure out which one is which, we go to the first sign. Since the first sign is addition, that means the bigger number is addition, and the smaller number is subtraction. So now, you can take x plus 3 equals 0, and x minus 2 is equal to 0. So x is equal to negative 3, and x is equal to positive 2. It's equal to positive 2. You don't even have to put the addition sign. But anyway, you need to check both these answers. Because remember, in a logarithm, we cannot have anything negative inside the logarithm. So if you were to plug this in, if you were to plug in negative 3, for instance, you would have log of negative 3 plus 6 minus log of negative 3 plus 2 equals log of negative 3. And this is where we check our answer. If you notice, this logarithm works, but these two have negative inputs, because negative 3 plus 2 would be negative 1. Those don't work. So negative 3 does not work. So now we have to check positive 2. If you plug in positive 2, you have log of 2 plus 6 minus log of 2 plus 2 equals log of 2. That 2 plus 6 is 8, so that works. 2 plus 2 is 4, so since that's positive, that works. And since log of 2 is, obviously the input is positive, so that works. So the only x value that works would be positive 2. Alright, so it says solve log base 2 of 3x minus 7 times x minus 4 equals 3 and give exact solutions. Alright, since we have log base 2 of something equals a constant, we can rewrite that as an exponential. Since the base is 2, that would be the base of our exponent. And the exponent would be the output, the 3. So it's 2 to the 3rd power equals the input, the 3x minus 7 times x minus 4. So if you multiply those together, if you multiply those factors together, you'll get that 2 to the 3rd, which is 8, is equal to 3x squared minus 19x plus 28. Now, you subtract 8 from both sides to get it equal to 0. So 0 is equal to 3x squared minus 19x plus 20. So now, we need to factor this quadratic. Alright, so we can do that by multiply the first and last terms. 3 times 20. 3 times 20 is 60. So we want the factors of 60 that add to give you 19. Alright, the factors of 60 that add to 19 are 4 and 15. But since it's negative 19, it'd be negative 4 plus negative 15. And now from here, after we have those numbers, you would divide by the leading coefficient. Since the leading coefficient is 3, you would divide both those by 3. So that would be x minus 4 over 3 times x minus 5 equals 0. Also, if you were to factor it, if I ever told you just to factor it, you'd move the 3 out in front. But since we're trying to solve for x, you don't need to, because all I'm concerned about is from here. Take both of these, set them equal to 0, and solve for x. There we go. I'm trying to get rid of that red 0. So anyway, if x minus 4/3 is equal to 0, and that's supposed to be a 0 on the end there. If x minus 4/3 is equal to 0, then x is equal to positive 4/3. And if x minus 5 is equal to 0, that means x is equal to 5. Now, I will tell you that if you were to plug both these back into the original logarithm, they would work. So, they both work. So both of these would be solutions. Now for the next example. ln of e raised to the power of ln of x minus ln of x minus 3 equals ln of 2. Excuse me. It says give the exact values. So since you have ln of e raised to some exponent for the very first term, this one would just simplify to the exponent, which is ln of x, minus ln of x minus 3 equals ln of 2. Now, since we're subtracting the logarithms on the left-hand side, we can combine them into one logarithm and divide x over x minus 3 equals ln of 2. So, now since you have two things that are equal and they're logarithms with the same base, you can take the inputs, the x over x minus 3, set equal to the other set equal to the other input, rather, which is 2. Now you gotta solve for x. To get rid of this, you need to multiply by the denominator, because you need the x out of the denominator in order to solve for it. So multiply both sides by x minus 3. Because then those would cancel out. So you end up with x equals 2 times x minus 3. if you distribute, you end up with x is equal to 2x, 2 times x minus 2 times 3, which is 6. So now, if you subtract 2x from both sides, those cancel out, so negative x is equal to negative 6. Now if you want to solve for x from here, you can divide by negative 1, get rid of the negative sign, so x is equal to positive 6. Or if you knew that negative x equals negative 6, then that should intuitively tell you that positive x would be positive 6. So now we're going to move on to a couple of word problems. The first one says the strength of a habit is a function of the number of times the habit is repeated. If n is the number of repetitions and h is the strength of the habit, then according to psychologist C.L. Hull, the strength of the habit is equal to 1,000 times 1 minus e raised to the power of negative k times n, where k is a constant. Solve the equation for the constant k. Alright, if we're going to solve for k, we first need to get rid of the parentheses. In order to do that, we need to distribute. So h is equal to 1,000 times 1 is 1,000 minus 1,000 times e raised to the power of negative k times n. Now we need to get the exponent term by itself. Do that, we need to subtract 1,000 from both sides. That would give us h minus 1,000 equals negative 1,000 times e raised to the power of negative k times n. Now, from here, you can divide both sides by negative 1,000 . Alright, so if you divide by negative 1,000, that would just leave you with e to a power of negative k times n. Now if you divide by negative 1,000 on the left, what you could do is split them up into separate fractions. Negative h over 1,000, or h over negative 1,000, doesn't matter, and then negative 1,000 divided by negative 1,000, which would be plus, since the negatives would cancel out, that would be plus 1,000 over 1,000. So that would simplify to, the 1,000 over 1,000 is of course 1 minus h over 1,000 equals e to a power of negative k times n. Now to get the k, since that's what we're looking for out of the exponent, you have to do natural log of both sides. Do natural log of the left-hand side too. And that should give you ln of 1 minus h over 1,000 equals negative k times n. Now to solve for k, you would divide by negative n, because that would cancel out both the n and the negative. So k would be equal to, let's see if I can bring that back down real quick. So k is equal to ln of 1 minus h over 1,000. Since we're dividing by negative n, Since we're dividing by negative n, that's the same as multiplying it by negative 1 over n. To write it on a new slide where I have more room, k is equal to, I think one of the ways we had it written was ln of 1 minus h of 1,000 over negative n, or k is equal to, since we're dividing by negative n, that'd be the same as negative 1 over n times ln of 1 minus h over 1,000. So either of those would work. Now, on to the final problem. The table gives U.S. coal consumption in quadrillions of British thermal units, or quads, for several years. The data can be modeled by the function f of t equals 24.92t minus 93.31 when time is greater than 80. Where t is the number of years after 1900 and f of t is in quads. And let me bring the table up now. Alright, so there's the time, or there's the table. And approximately what amount of coal was consumed in 2003? And how does this compare to the actual figure of 22.32 quads? Alright, so for part A, if it happened in 2003, since t is the number of years after 1900, t would be 103. So if we plug 103 into our formula, that would be 24.92 times natural log of 103 minus 93.31. So if you type that into your calculator, you should get that the approximate amount of quads would be 22.19 quads. Now this is to compare to the 22.32, so it's very close to the actual. It's very close to the actual amount. And for part B, it asks if this trend continues, approximately when will the annual consumption reach 25 quads? So if it's asking when, we're looking for the t, which means 25 gets plugged in for f of t. So instead of f of t, the amount of quads would actually be 25 equals 24.92 times ln of t minus 93.31. Now we gotta solve for t. Since we're subtracting 93.31, we would add Alright, so if you add that, those would cancel out, so the left-hand side would just simplify to 24.92 times natural log of t, and 25 plus 93.31 would be 118.31. So now you gotta solve for ln of t, get the natural log by itself. So divide by 24.92. So that tells you the left-hand side simplifies to ln of t equals, you can just leave it as a fraction, 118.31 over 24.92. Now remember, ln of t, since our variable is inside the logarithm, let's rewrite this. It might be easier for some of y'all watching to see. Rewrite as log base e of t. So what we can do here is take the base of our logarithm, rewrite it as an exponent. So it'd be e to a power of 1 the exponent would be the output for the logarithm, so it would be 118.31 divided by 24.92. Alright, and that's equal to the input of the logarithm, which is just t. So if you type all that into your calculator, e raised to a power of 118.31 divided by 24.92, that would tell you the approximate amount of time after 1900. So typing that in gives you t is approximately 115. This is actually 115.306. So approximately, remember that's the time after 1900, so it's approximately in 2015. Approximately in the year 2015 or 2016, it will be at least 25 quads.